People at the back, can you hear me loud and clear? Awesome. Okay, so let's get started. Today is the last lecture on HMMs, and today, next Monday, we'll be starting lecture 9 on natural language understanding with Zinning, my co-instructor. So today will be my last lecture with you folks as well. So it's been a great pleasure, and I'll take some questions at the end of this lecture. Today will be a relatively shorter lecture. In terms of logistics, there isn't anything new. The assignment 2 is due on this Friday. I have updated the course web page with remark and extension policy. A notification was also sent on Quarkus. Please review it if the matter applies to you. May I get a show of hands? How many of you have A1 related questions? Okay, so a few. Okay, so I have forwarded the questions. So the A1 head TAs are, and Professor Lee, like they're aware of the questions and they're working on it, and hopefully you'll be getting an answer soon. And today's officers are mostly for assignment 2 questions, but I'll check if it's possible for someone from A1 to be at the office hours as well after this lecture. I'll forward that request as well. Yeah, so, okay. All right, so let me start with today's proceedings. So we have seen this slide last lecture. Just want to do a quick recap to get in the flow. So we have 3 tasks for HMMs, and we've looked at task 1, task 2, and last lecture we started task 3, which was the task of training. You're given a set of observations, and then you're trying to update your model parameters theta, which comprises of pi AB, initial state probabilities or transition probabilities, and the emission probabilities. All right. And the reason why we want to do this is essentially if we have a trained model, then we can solve other tasks. For example, choosing the best sequence Q star for previously unseen test data. So this is the task 2. So in order to solve the task of inference, we need to have a trained model, and that is the task of the current task, or which is task 3, the model training. Okay, so a reminder that we're dealing with hidden Markov models, so the states are hidden. And if we had, like, we're trying to decipher this joint probability of observations and states, and if we had the states in our training data, then it's not a hard problem. We can just do a maximum likelihood estimation, like the way we did it for language modeling tasks per se. Okay, yeah, so this slide again reiterates that if we had state sequences, we could have just done an MLE and be done with it, but we don't have that. Okay? And that's why we will be doing an expectation maximization algorithm to iteratively update our theta. And the way we can do it is in 2 iterating process. In the expectation phase, we get the values given our current theta k at that iteration k. We get the expected number of like times we're in state I and the transition expectation, and then we use that in the maximization step to calculate theta k plus 1, and then we go back to the expectation step and so on. Okay, so we have seen the expectation and maximization steps and their duties. And the convergence can be a heuristic convergence criteria. Popular criteria is there where we don't see much change between 2 iterations, then we say that we're done. The model is not improving much, so we can call it a day. Other convergence criteria could be just the number of iterations. We can say that we will be doing this model feeding or training for 50 iterations, and then we're done. Okay, so this slide shows the main steps for the Baum-Welch re-estimation. So we initialize the model, then we have expectation step, then the maximization step where we update our theta parameters, and then we go back to 2 and repeat them. And as a reminder that the one con of using this kind of approach is that we're never guaranteed the optimal solution. depending on our initialization, we can end up in a local maxima. Thus, the Baum-Welch initialization becomes an important decision, and there's few ways we can do this. One way is to do just uniform probabilities. So here we can see that each of the states' emission probabilities, they're just uniformly divided or proportioned. The other way we can do this is using a random initialization where we assign random probabilities, emission probabilities to our observations in each state, with the only condition that they are a valid probability distribution, that is the sum of all these emission probabilities equates to 1. And the third way to do this is we can use some kind of prior distributions. So we can take our data and then perform some kind of pre-clustering algorithm, like k-means clustering, and then cluster our data points into the number of states that we have guessed, and then use those data for each of those states in order to assign our emission probability for that state. So in this case, let's say all the blue states, all the blue dots are some observation belonging to the state blue. And then we say that, okay, so if that's the case, then we will assign our emission probability by using only this data belonging to this cluster. And we do the same for the other two, other two states. Okay, so now let's take a look at the expectation or the E step. The E step has two parts. The first one is occupation. And the occupation, we introduce another Greek variable, gamma it. And gamma it essentially says that the probability of being in state I at time t based on our current model theta k and our observation omicron, like our entire observation. And the bottom part shows mathematical formalization of this. And here we can see the forward and backward procedure values alpha I and beta I that we had seen in our first task. Now, remember that this alpha it and beta it depend on the values of theta. So if your in current iteration is k, so this is like alpha it, beta it corresponding to that theta k. This is a pictorial depiction of the trellis probability. And yeah. Okay, and the second part is the transition step in the expectation in our E step, and we have another Greek alphabet, xi I j, which basically says the probability of transitioning from state I to at time t to state j in state t plus 1 based on our current model theta k. Okay, and this is just a mathematical formalization. This is a decomposition using our known variables with respect to HMMs, and the denominator here is just like normalizing, the likelihood observation is normalizing to make it a proper probability distribution. Okay, and this is a pictorial depiction of the transition process. So we already know this arc probability. So then alpha I should capture all our the forward-going probabilities, and beta j captures, coming from right to left, the backward probability. And then this arrow here is the arc probability, and this is intuitive that you have the transition probability times the emission probability of observing whatever we're observing in t plus 1. Okay, so now let's take a look at the maximization step. So note that when we're in the maximization step, we have the values of gamma it and xi ijt from our expectation step. Okay, so we're going to use that to compute or update our parameters. And how we can do that? And this slide shows that how we can update our parameters to get theta k plus 1 from our values from theta k. Okay, so the initial state probability, the gamma is just pi is just gamma I 0. So if you think about like observation sequences, then it's actually gamma I 0 over 1. So there's only one way you can start. So you can take the first step's gamma I 0, that gives our initial state probabilities. And for state transition probability, think of it as basically like counting the number of times This is exactly what we did for language modeling as well. So the number of times we're transitioning from I to J, and the number of times we're actually in state I. Okay, so and you can see that we're going from 0 to t minus 1 because t minus 2, t minus 1 is our ultimate step, so this penultimate step, and after, like, there's no transition in the last time step. So we just stop at t minus 2. The same thing with the emission probability. So here we're just basically doing an Emily estimation, which reads out as this, that how many times have we observed certain word I when we're in a certain state, and that normalized by the total number of times we have been in that state. Okay? So once we do this, we have new values, pi, A, and B. And this is our theta k plus 1. Okay? And yeah, so we update our parameters, and then we basically use this theta k plus 1. We go to the expectation step and use that theta k plus 1 values to recount all the values, and then like basically calculate gamma it and psi ijt, and then use those to come back to get theta k plus 2 and so on. So the Baum proved this here. It basically reads out as at every iteration, we are getting some improvement, at least as good as the previous model parameters. Although it does not guarantee a global maximum because it's a con with iterative hill climbing, the initialization matters, and you could be stuck in a local maxima. Okay. Some features of Baum-Welch. It's not guaranteed to achieve global optimum, which we talked about, but the local optimum are often good enough for the task that it's designed to do. And Baum-Welch does not estimate the number of states, which must be known beforehand. So yeah, it's the hidden states, so it's hidden, so we don't really know it from before. However, we can introduce some constraint over the topology of the state transition, as you have seen in previous example, the running example with like sad, disgusted, and happy state. So you assign some transition probability to put some constraints on this non-stationary underlying hidden states. And this HMM generalizes to continuous domain problems as well. In fact, in this course, in assignment 3, one of the assignments was to formulate like HMM-based, like GMM HMM speaker identification problem. So as observation, you'd have acoustic data, which is like MFCC coefficients, and then you'd use that, and you'd be given like you have n speakers. I think the n value is 8, and then you basically identified that given a sample, which speaker is it coming from. So it is possible to solve continuous domain problems with HMMs, and the probabilities, emission probabilities, and everything will be like continuous as well. Okay, so it takes a lot of data to train HMMs. So one caveat of this is that, or because of that, it is very important that we are able to reuse our trained HMMs once we have trained it. So let's go with the running example of speaker identification. So we have a lot of data, it takes a lot of time, we train it. And then someone comes and says that, okay, we have new data, but this corresponds to a new person. Can you basically train your model and include this person as well? So do we throw out our entire training from before? No, we don't want to do that. We want to update our trained model because it's expensive. We've already trained a model. So somehow incorporate the new data and a new person into our in an updated model. Okay. So what we want to do is that we want to change the original HMM parameter slightly given the new data. And the next couple of slides talks about how we can go about it. Okay, so we can apply interpolation, which is basically assigning a weight to our different models. So, for example, I'll go with the running example that I've been using with n speaker identification. So we have trained 8 speakers, which we call the generic HMM or G. And then we're given a new data for this new person. We call it specific HMM S, okay, for a single source. So we can, easy way to do this is that we can say that we'll use a sort of mixture of XPART or interpolated model where we assign weights to each of the trained HMMs. Okay? So then that gives us a model tuned to our target source S, but with some general knowledge G built in. The subsequent obvious question is that then how do you pick this lambda or the weight value between the models? So we can use the strategy of, so here the equation, like, the total observation based on our lambda values will be like, a summation of like each of the models, so the interpolated models. So if we can introduce some kind of a meta state such that that's like an identifier for state. So if we can say that, if S equals to I, then we know that it belongs to model I or like HMM model I. So we call it lambda Y. So if we can do something like that, then we can basically train this lambda parameters using expectation maximization, because we can estimate like the count, like how many times we see this meta state. And then if we can do that, then we can basically update lambda I. So consider lambda I as being our theta, and we have our observations, and we can sort of train lambda I values just like we did EM. Yeah?
Sorry, in this setting, when we talk about adding a new speaker, does it mean that a new speaker is a new state? What is it?
In this case, the hidden states are the speakers. So you have MFCC data, some acoustic signals, and you train your model, and then your task of inference is that you say which speaker is this MFCC data like correspond to. Now, then let's say you have a new HMM model trained on MFCC acoustics just on that one person, which you can say that like theta S, okay, single source. And we already have like theta G trained on all the speakers. So that's the setup.
These two models, they have different state spaces.
Yes, yes, they do. Yeah, yeah. Think of it as, I would say more of, like you're introducing another extra hidden state with some more data that corresponds to just that hidden state. Like, so did we cover Jelinek-Mercer interpolation in language modeling? I know that there's language model interpolation earlier in the course in second or third lecture. So the idea is this: think of you have a unigram model, bigram model, and a trigram model. Okay, and in order to, and we know that trigram model is better than bigram model in terms of perplexity. And bigram model is better than a unigram model in terms of perplexity. So the observation likelihood or the probability is better, essentially. So what we're trying to do is that give me an answer, but interpolate between these three models, okay? And then the question is that, okay, so what weight should I assign to each of these models? Like how much weight, unigram, bigram, and trigram. And this is like, we're trying to do sort of the same thing, consider the language model. Instead of the language model, think of like an HMM model, right? But then there's a caveat. The caveat is that how do you use the data? Like, so which data do you use? So it's very important to have held out data set for training each of, or while we're configuring this lambda values, we have to use held out data. The reason being is, I think it's much intuitive if I give an example. So, right. So if, let's say we're trying to do, so lambda 1 is LM unigram plus lambda 2 is LM bigram plus lambda 3 is LM trigram. Okay, and this is our entire observation. Now, if we're trying to figure out something, I believe, like how do we assign our lambda or the probabilities, okay? Sorry, this is not going to be the probability, but that's our goal. That how do we assign the right weights? So these are our three models, and we're going to do an interpolation between them. So the main idea of this slide is if we don't use held out data, then this guy will always win. And if we like, solve like based on the entire observation, so then the weighting will be like 0.01 or whatever, very negligible values, and this will be like 0.99 LM3, because this has a superior performance. So this is not a fair comparison. So that's the notion of this this slide over here. The same thing is like if you have for the speaker identification, you have like a generic observation data set, and you have a single source observation data set. And then, yeah, so basically, if you're gonna do an interpolation, then like if you do it on the entire, so you get the point, right? So because whatever the superior model is, if you don't have a held out data set, then that superior model will win out, and then the whole process of calculating lambda weights, interpolation weights, becomes meaningless. And this is also sort of the same idea as any other training. The reason why you split your data set into train or development and tests. So essentially the same idea. This is a side slide, but I'm pretty sure you're already very familiar with this concept, maximum a posteriori probability. You can think of MLE, but you have a prior probability distribution P theta, which allows you to basically introduce a bias, or like how you want your theta to be trained. Yeah. And the notion of Dirichlet distribution. So Dirichlet distribution is one possible prior distribution that you can use in the continuous space. I'll do something experimental today, like at the end of the slides, I'll try to do like a coding example, like an illustration of how you can actually apply HMM, so that this sort of makes sense a bit more concretely. And we'll see that how we can use like the Dirichlet distribution to just assign a prior probability. Okay, and this slide essentially says that HMMs are generative models and not discriminative ones. You know what discriminative models are. Discriminative models are classifiers. For example, like you have image classifiers. So you're given an image of cats and dogs, you train on it, and you say whether it's cat or a dog. But HMMs are not that. It's more of a generative classifier, because given the model, you can generate sequences. All right, so in summary, for the final exam and in summary, the main things that you need to understand is, first of all, like, what are the three main problems that HMMs are trying to solve and why? And then obviously know the details of, the forward-backward algorithm, the Viterbi algorithm, and the Baum-Welch algorithm. We're not gonna ask you to solve like an EM algorithm on paper, but like some understanding of what is expectation maximum, which probably you already know, and then some understanding of the equations. Okay, so these are some readings. These are all already on the course website under the handout. I really suggest this one. This is a very classic paper if you're interested in HMMs. And I want to, so for the illustration, I want to set up the problem like this. So so let's say if you go to a casino, and then you observe the roll of their dice, and after some time, it seems like certain number is coming up more than, like, it's a loaded die. You have a intuitive like sort of suspicion, okay? And then can you use what we learned in HMMs to find out or test that hypothesis? So this is the setup. We're saying that, like, this is the actual situation. So the casino basically loads a die to roll sixes more than the other numbers, but they don't do it all the time because they're going to get caught. So they use the fair die 95% of the time, and with 5% probability, they go to this loaded cheating state where they use this emission probability on the right. So the first emission probability is like a fair die, and the second one is loaded, which is biased towards the number 6. In the code, 6 will appear as 5 because it's 0 indexed. Okay, any questions on the setup? Okay. All right, so all right. So this is taken from this book. And okay, so at first, before we do anything, we will generate some observations. So these observations are real life observations. You're observing this at a casino. How we can do this is that we can define a categorical HMM with two components, fair and loaded. They're the two states and with some random seed. And here we are basically, defining our pi, our theta model parameters. So the initial start probability is we always start in fair because we don't want to get caught, or the casino doesn't want to get caught. And then the transition probability is just codification of the diagram that we have seen. And yeah. And then we have the emission probability, or B, or the parameter B, which is again the codification of what we have seen on the diagram. Okay. So you can now use this casino model to generate lots of data. So we generate 30,000 samples. And then I have printed out 20 random samples from, so we get the roles and the generated states. So here you can see that the generated states, so 0 signifies fair state and 1 signifies loaded state. So as per our knowledge, we know that when we are in the loaded state, we expect to see about 50% of the time we want to see 5, right? And so here in this case, I would say would see 3 or 4 5s being rolled.
5 or 6?
It's 0 index, so when you see 5, it's 6. Okay, everyone with me? Okay, so this is the same corresponding 20 rolls, and if we see, so here, I think there's 4 5s. So this actually, so it is working. So in this loaded state, you're seeing 50% of the time, you're seeing a roll of 6 or 5 in 0 indexed. Okay, so let's plot this up. So the first plot essentially shows for the first 500 rolls, how do the states change? So this just shows 0 is fair, 1 is loaded, it's just switching states, and this gives a better idea. So we'll take all the rolls and all the states, and then we'll just plot the probability of the rolls, and we expect to see the difference, and this is right. So when it's in fair, the probability of each of the rolls is 1/6 or 0.167. And when you're loaded state, 0 to 4 is 10% and 5 is 50%. Okay? All right. So these are our observations. These are given to us. Now you go in and you're saying that, okay, so let's apply HMM. So first is that given the observations, I want to train my model. And that is the expectation maximization. So what I do is I split the data into training and validation sets. And I get from our validation, so we have a true score, and I'm trying to calculate the best score or the best model, okay? And then essentially this is a EM algorithm. We apply training for 50 iterations. Here our convergence criteria is number of iterations, okay? And we feed the train and basically the basic training process, and then we basically train the best parameters. Okay, we do it 50 steps. Ignore the score. It's just relative. We have achieved after 50 iterations, we have our theta parameters, or we have a trained HMM. Okay, so then what we can do is that we can use that trained parameters to predict the most likely sequences of states. Okay, so here the task 2 or Viterbi algorithm. And the Viterbi algorithm is all, of course, happening underneath in the library, so we're not going to get into that, but we're calling predict on the roles, and that gives us the predicted states. And this diagram shows basically...
Sorry, I was just kind of a bit disappointed with how well it works, because
okay.
There's a huge difference.
Yeah. Yeah, so this, I think it's what's important to see is that if we look at the predicted transition probabilities, transition matrix. So this is the true transition matrix that we have started with the figure. And after training, this is our our model's predicted transition matrix. And as you can see that this is pretty close. We can easily guess that there's two states and something fishy going on, and it's very close to the actual true transition matrix. Okay. And the final question is how we can see if the tie is loaded. We look at the true emission matrix and the emission matrix predicted by our model. And here we can see that in our emission matrix predicted, we can see that one of the states, they're almost like they're equally probable, looks like a fair die. But if we look at the other state, we can easily see that one of the states has a significant discrepancy from all the other states, signifying that there is a loaded state. Okay? And yeah, so that's it. That's a very simple example. I wanted to do like a GMM, HMM example, but I don't think we have the scope or time for that. Maybe the time, but not, it's kind of like it's a little bit more involved. You have to use continuous domain data like MFC data, loading and training. It's going to take some time, but yeah. So I hope that this is a very simple sort of toy example gives you a better, concrete grasp of why or how we can use HMMs. Yeah.
And when you ran it, like approximately, how long did it take? Like,
this one very fast. It wasn't. Yeah, sure. I can just try it right now. So 30,000 samples. Yeah, it's so this guy takes a little bit, not that much. Is it running? Yeah, so see, it's pretty fast. So we could have done 500 and see. Actually, why don't we do 500? 500 was the wrong choice. I'll tell you, sure, let it run in the background. Okay, so yeah, so that's it for HMMs. Thank you so much for being with me for the last few weeks, and it's been a pleasure. Good luck with assignment 2, and I'll see you on the final exam date. Okay, thank you.